All right. It even has some chapter 3, like the Venn diagrams in it. So keep that in mind. Okay, so 4.1, counting principles. If one task can be performed a number of ways, okay, and a second task can be performed in b number of ways, then the two tasks together can be performed in a times b number of ways. I also want you to think of ways. I want you to think of, not ways, my bad, tasks. Tasks, I want you to think of events, because I used both of them. I actually probably use events more so than tasks. Okay, so if you had, if you have, like me, just two shirts and 3 shorts, right? Then the number of outfits I can probably have would be 2 times 3, 6 different outfits. Okay, so that's the idea here. In general, if you want to know the total outcomes possible, just multiply the option by each event, okay? Total number of outcomes, just multiply the options for each event by the others. And this is called the fundamental counting principle, FCP. I use this a lot, okay? For tasks that are related with the word and, we multiply, okay? For tasks that are related with the word or, when you kind of either read that it's an or scenario or it's explicitly said, then you want to add, okay? So for example, a password may start with an A or a B, or, okay, it can start with A or B, or a password can have 4 characters or 5 characters. Oh, there's the or. So you're going to have to do some adding there. And so using the principle of inclusion and exclusion, pi formula, it is important to note that sometimes or is implicit, not explicit, so sometimes it's not obvious, right? And this still stays. I'm going to show you when this happens. But when you're trying to figure out number of events for task A, number of events for task B, there may be overlap. We have to subtract, right? Subtract any overlap. Okay? So, in a sense, if you have your Venn diagram with the A and the B, and there's the number of events of A and B, you do not want to count whatever is already in B, you do not want to count it in A. For example, this is on the fly here, I'm trying to think of one. If A were to be the number of red cards, and B would be your diamond cards, is that a good example? Sort of. No, I think it would be face cards and diamonds. But anyways, like if I won't make one up now because it might contradict. I'll think of one later. But if there's any overlap between the two sets that you're adding up, like your events, you want to subtract the overlap. And I'll show you when that happens down the road. If the sets are, right, if it's joint, rolling die and deck of cards, there's a lot of overlap, so we need to watch out for that. If it's disjoint, then the intersection is just 0, so we don't have to worry about it. I just want you to be aware of it. I don't use these formulas a whole lot. I just want you to be aware of it, that that's still coming with us, right? So disjoint. This could be your even and your odds, let's say. If you're adding up the events in A, which represent even numbers, and the events in B, which represent the odd numbers, if you were to add, you would not have to worry about any overlap whatsoever. Okay. Maybe I just came up with an example. If this would be your prime, and this would be your even numbers, prime and even, what's in the middle here? What are they both count? You would be counting the number 2 twice, correct? And so you'd have to subtract that overlap so you're not double counting. That's all I'm saying. So let's apply this. Flipping a coin and rolling a 4-sided die. So task 1, task/event number 1 would be coin, and task/event 2 would be a 4-sided die. Okay. How many outcomes are possible? What is the sample space? Show using a tree diagram, an outcome table, and fundamental counting principle. You're saying what, right? So this is how, I'm sure you've done tree diagrams before, and it is as easy as you will see me do it here. You decide which one you want to start with. I'm going to start with the coin. So this would be heads and tails. And your second event has it's a 4-sided die, right? So you go 1, 2, 3, 4. And off of the tails, you also have 1, 2, 3, 4. And look up here real quick. You could have flip the coin and land on heads and get a 1, right? Or you could land on tails and get a 1, right? So there's a bit of an or happening when they branch off. So this is your outcome. This is your sample space right here. Flipping the coin, getting a head and 1. This would be one of the possible outcomes. Head 2, head 3, head 4. Okay, so 4 outcomes already. Or you could get tail 1, tail 2, tail and 3, a tail and a 4. Okay, so this is your, if you think about it, there's 8 outcomes. And this is what we call the sample space. Sample space. So there's 8 possible. This is like our universal set, guys, okay? This is all possible outcomes. So this is the tree diagram. I'm just going to go tree here. I don't have a lot of space. I'm just saying, if I ask you for a tree diagram, I just want you to do this. Let's make a deal. If I don't say with the outcome table or the possible outcomes, then this would be enough for me. Like, you get your mark there. But if I do mention indicating all possible outcomes, then I actually want you to add that part to it. And you do whatever you need to do. You can go heads, write out heads, and go heads 1. It doesn't matter. Shorten it, whatever you must do. Let's do the outcome table. Where is that? Outcome table, let's do that next. Outcome table only works when there's 2 outcomes. So you can have 1, 2, 3, 4 down, like one of the events goes down here and the other one goes up here. So you'd have heads or tails. So as the name suggests, you have an outcome table. So you go H1, H2, H3, H4, tail 1, tail 2, tail 3, and tail 4. So again, this is your outcome sample space right here. And how many are there? There are 8 outcomes. And all of this just to show you the easy way. That's called the fundamental counting principle, where you just go task 1. That's your coin, right? There's only 2 possible outcomes. And task 2, even this is overkill. Like, you wouldn't have to do all of this if I asked you this on an AC quiz test. This would be your die, right? And there are 4, because it's a 4-sided, there are 4 outcomes. Therefore, 8 outcomes. What the fundamental counting principle is not good at is showing you all the possible outcomes. It just shows you how many in total. But all of them essentially conclude that there's 8. Right? All of them showed us that there's an 8. That's the universal set, in a sense. So tree, outcome table, confirming what we've done using the fundamental counting principle. And then the second one, suppose you're flipping 3 coins at the same time. How many possible outcomes are there? Use a tree diagram, then confirm with the fundamental counting principle. So a tree diagram allows you to analyze more than just 2 events. You're flipping 3 coins. Okay, so coin number 1 can land on heads or tails, and then coin number 2 gets tacked on. So this is your second event. Okay, heads or tails, heads or tails, and then our third event. Heads, tails, heads, tails. I would suggest keep a pattern. If you're starting with heads and tails, continue that pattern. It's much easier to see what's happening. And so this would be all heads. This would be heads, heads, tails. This would be, I hope you understand. Look up here just 1 second. I go right heads, tails, heads. So you're basically reading how you got to this particular branch. Then it's heads, tails, tails. And then we go down this branch. Tails, heads, heads. Tails, head, tails. Tails, tails, heads. And all tails. Check. How many outcomes? 2, 4, 6, 8. How so? If you use the fundamental counting principle, this would be your coin number 1 times coin number 2 times coin number 3. So each one of them in this case has the same number. It's all 2, unless you have a 3-sided coin. I don't know if there's such a thing. 2, 2, 2. So that'd be 8 outcomes. So confirmed. This is a quick way to confirm, are you doing this right? So tree diagrams are quite popular. How many outcomes have all tails? It should be easy. 1 out of 8, right? Just 1 here. All heads, that's your extreme here. Look at how slow that is. Heads is right here. How many outcomes, listen carefully, how many outcomes have exactly 1 tail? Exactly 1 tail. I'll just put a little dot here. 1, 2, 3, 3, right? How many outcomes have at least 1 tail? I'll do 2 dots. At least 1, right? 7, yes. Because if you start here, 1 tail, 1 tail, 2 tails, 1 tail, 2 tails, but anything from here on in have at least 1 tail. So actually all 7 here. And so I can ask you questions like that, and that's where the and is when you multiply and the or is when you add. Okay, so that's how we deal with that. Let's keep going. I want to get to the passwords. We're going to have lots of fun with passwords and license plates and postal codes and all that stuff. I don't know if you remember the time where they made you use the area code 204, right? And then they went 431. Is there another one now? I feel like there's another one for Manitoba. I think they introduced another one. But that was because they were running out of numbers, right, to assign. So the more options you add, the more possibilities you have to come up with that phone number. Okay. Stephen plays soccer. His team has 3 jerseys, 2 pairs of shorts. How many different outfits combinations are possible? Draw a tree diagram, show all your outcomes. I wonder if I'm going to leave this one for you right now. I'm going to put a star there because by now you should know how to do that. So example 3 as well as part B, we're going to leave that for now. I may come back to it later. Let's go to that example here with the combinations and passwords and whatnot. A luggage lock has a 3-digit code in which each digit can be from 0 to 9. How many digits do you have if it's from 0 to 9, by the way? How many options? 10. 1 to 9 would be 9. 0 to 9 would be 10 options. Okay. You got to read these very carefully. Sometimes it's 1 to 9. Sometimes it's 0 to 9. 1 to 8. You got to watch out. How many possible combinations? How many possible combinations are possible? Too much possible there, right? But how many combinations are possible if there are no restrictions set whatsoever? Repetition is allowed. Okay. So watch this. You have a 3-digit code. So you've got 3 slots to fill in, and you have 10 options for every single one. That would just be 10 to the power of 3. Sometimes I'll use this to make it quicker. And that would be 1,000, right? Passwords. You can go combinations, passwords, whatever you want to fill in there. I'm fine with that. Watch this here. This is important. Repetition is allowed. So you may have a password that's 000. You may have a password that's 111. Okay. Repetition is not allowed. How would this change? So you're still back to the original 3-digit code, but now you're making one, they're putting a restriction on you. By the way, nowadays they do that more and more, right? When you create an account online, it must have this, it must have that, it must, right? Those are restrictions. You can't just do whatever you want. Okay, so repetition is not allowed. What does that mean? That means I have 10 options for my first digit. How many are left after I've used one? I'm down to 9. I have used one here out of the 9, I've used one. Now I only have 8 options left. So that's when there's no repetition allowed. Okay. Not allowed, then it drops every time. That's how it's different. Repetition and no repetition, I have them right next to each other. And so you do that. So you just go 10 times 9, that's 9 times 8 is 72, times 10 is 720. Passwords. Okay. So we're gonna try this. Hold on. I think this one I just added right now. I'm gonna go with this one here. Only digits 1 to 8 can be used without repetition. One to 8 means how many options? 8 options. Okay. That's all you have. And you cannot repeat. If it had been with repetition allowed, you just go 8, 8, 8. Right? Can't do that here. So you got to go 8 times 7 times 6. doing this ensures that you're not counting the ones that have repeated digits. You know what I mean? That's what this step does. Okay. And I know it's a bit of a weird concept. I get it. Always ask yourself, what's the greatest amount of passwords that are possible in this? At the very beginning, we had 1,000. Every time you put a restriction on it, you drop. So when you do these types of questions, you shouldn't have a scenario where you have more than 1,000, right? That's absolutely the highest. This is universal. This is your universal set right here, okay? The first number cannot be 0. Repetition is allowed. What's going on here? So we're still always dealing with that 3-digit code. First number cannot be 0. So you cannot have a 0 here. And by the way, you still, if it doesn't say anything, you have 0 to 9 normally. So if you cannot use 0, you have 9 options, correct? What would this be? 0's back in the game. You still have 9. Okay? And now you need to drop 1 from this. Okay? 0 is back. Okay, that's what's happening here. So you had 10 here, but you used 1 here. Think about it, right? Technically, you have 10 options here. 10 options. But then we say, no, we cannot use the 0 on the first one. So for the first one, you only have 9. But you are using 1 from your 10. Right? So technically, you have 8. But then, hey, the 0's back. So you're back to 9. And then 8. And so you got to drop from there. Does that make sense? No? You want me to do this a long way? Okay, hold on. I'm going to do this down here. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so there's 10 options here. But on the first one, they're saying I can't use this one. So how many options do you have for the first one? 9, right? So you're using 1 up. So how many options are left for the second one? What's that? Sorry, guys. That's what I missed. Sorry about that. I don't know what I should change. Should I change repetition not allowed? Because this is going to mess everything up. Repetition not allowed. Sorry about that. So can I cross this out here? Yeah, sorry about that. Does this make sense though if repetition is not allowed? Does this make sense? Okay. So 9, 9, 8. Yes. So you're going to have to practice a bit and maybe hopefully your teacher doesn't mess you up like this. Okay. This one here, how many codes would have at least 1 repeated digit? This one right here, I want you to put a star there. And I'm going to highlight that one as well. When you see that one, remember earlier when I asked you at least 1 tail? You remember that one? Let's go back to this one here, the heads and tails. When I asked you how many examples have at least 1 tail, and then we counted all 7, right? This one was the only one that didn't pertain. All heads is the only one that didn't have at least 1 tail. That's called indirect reasoning. So I want you to think of it that way. I want you to think of it this way. We're going to go total outcomes minus no repeats. Okay. If you take your total number of outcomes and you take away the repeats, the ones that possibly have one or more repeated letters, right? If you take away the ones that have no repeats, you're going to be left with all of the ones that have at least one repeated digit. What are my total number of outcomes? It's 1,000. Okay. Minus. How many passwords have no repeated digits? They're right here, actually. I did this right here. 1,000 minus 720. Okay. So that's 280 passwords have at least one repeated digit. And I would like to have a color matching here. This 1,000 is my total, no restrictions whatsoever. And the 720 so these 280 may have one repetition, two repetition, or have all three repeated. Okay, that's what this is indicating here. Okay, so this is what we call indirect reasoning. And I'll tell you why you want to be using this one. Because finding out all possible scenarios that you have repetition would be very difficult. And if you miss one, you're off. You're done. You missed one, and it's a lot more work. Whereas if you approach it this way, where it's like, well, how many passwords are there in total? There's 1,000. Let's take away the ones that have no repetition. Okay? Then we're left with everything else. That's what they're asking for. Like, what's that everything else? That's the 280 passwords. So I added this. You're the first group that gets to see this because down the road I use that a lot. So I kind of want you to even bubble this in like this. I think this is a very important concept for you to understand that one. So if you see the word at least, how many have at least one? Focus, well, let's do the ones that have no repeats. Let's take that away from my total and then approach it that way. Trust me, it'll come your way multiple times throughout this unit. Okay. Page 4. Let's go there. We're still dealing with the 3-digit code, by the way. Still dealing with that. Okay. You would like the code to end in an even number. It doesn't say whether or not repetition is allowed, correct? We are assuming repetition is allowed if it doesn't say it explicitly. Okay, so we're going to go repeats allowed. Okay, we're assuming that here. So when it gives you some sort of restriction, you deal with that first. So if it ends with an even number, it has to end with a 0, 2, 4, 6, 8. Okay. It has to, so how many options do you have for the end here? 1, 2, 3, 4, 5. There's only 5 options to fill in this. So I kind of start with that. I fulfill my restriction and then I fill in the rest. So here you have 10. Here you have 10. Here you only have 5. Okay. So what would that be? 500? I'm just going to add this for you here. You have 0 to 9 here. You have 0 to 9 to fill in here. But here you only have these 5 options. Okay. The first number starts with a 3 or a 2. Repetition is allowed. Cases. What does that mean? the or. Let me show it to you in two different ways. I will say it starts with a 2. Here you have 0 to 9, 0 to 9. So if it starts, sorry, let's do with a 3. 3, that's just one option that you have there. Here you have 10, here you have 10. So that is 100 passwords that start with a 3. But then you also have to consider the scenario where you start with a 2. You only have one option there, 0 to 9, 0 to 9. So this is 10 times 10. Let's put a big OR here. So you're basically saying it's either going to start with a 3 or start with a 2. I need to account for both of those. So you get another 100 passwords here. So this goes back to the logic. A password has to start with a 3 or a 2, which means that you have a combined of, right, plus 200 passwords are possible because you're saying or. Okay. This is the long version. This is a method 2. I would just do this. You just tell yourself your options for the first are that you have 2 options, right? 2 or 3. And then you have 10 and 10, because for the other ones you can use 0 to 9. What are you going to get there? 2 times 10 times 10? Still 200. You may use a digit more than once, but you cannot have all 3 digits the same. Okay, so you cannot, example, this is a no-no. You can't have all 3 the same. How would you do that one? I would say this. Let's deal with this indirectly. If you have no restrictions, you would go like this. This is 1,000. No restriction. Okay. How many of these passwords are possible where all 3 are the same? It would be 0, 0, 0. It would be 1, 1, 1. How many passwords do you think there would be? 10, right? I'll just go dot, dot, dot. The very last one would be 9, 9, 9, right? So there's 10 passwords that have all 3 the same. So how many passwords would we be allowed in this circumstance? 1,000 minus the 10. So you're left with 990. So allowed would be 1,000 minus the 10. So that would be 990 passwords. This is also a newer one that I came across the other day from a textbook. I thought that got me thinking pretty good. So there will be times where I will be scratching my head too if you come up to me, because I will have to read it and make sure I get it right, as you are well aware of already. H. Your codes have to be greater than 600 and no repetition allowed. This is important, right? They have to be greater than 600. No repetition is allowed. Let's go back to our 3-digit, because this is what we're dealing with again and again. You have to fill in those 3 somehow to make that happen. Well, what are your options for the first? You can go 6, 7, 8, 9, correct? But I would say there's a bit of a problem here. If this is 6, and then ends up with a 0, like 600, that could be an issue, but you're not allowed to repeat. You know what I mean? You're not allowed repetition. So in this case, it's not a problem. Okay. So how many options do you have? 1, 2, 3, 4. Here you can use 0 to 9 if you'd like, and here you can use 0 to 9 if you'd like. I'll give you a little bit of time to fill this in right now. Think about it. If no repetition is allowed, what would be the numbers that go here and here? And I'm also going to ask you to try I and J. And if you get it wrong right now, big deal. Not a big deal at all. I just want you to try and approach what I'm doing the way I've been doing it, and see if you can come up with something. Like just see like what numbers, what digits would I put down to come up with my answer, okay? So I'm gonna leave this up to you for a little bit. There's the 2 or the 3 again, we've done that. That way you're not just listening to me and falling asleep, right? So try these 3 here, and I'll be back with you in a bit. I'll take it back here. So no repetition allowed. So 6, 7, 8, 9. So you only have 4 options here. Here you have to be careful. We're assuming that you only used 1 digit for this. Okay. So then technically you're back here and you would have 9. Okay. And then you would have 8 here. No repetition allowed. So don't be... I have a lot of students go 10 minus 4 and they'll go 6 here or something. Always remember, these are your options here. You only have 4, but you removed 1 of these from your 10. That's why you're down to 9 for the second spot and then 8 for this one. Okay, and so that's how that works. I'll just make a note here. You only use 1 of these, okay? Even though you put a 4 there, you're only using 1 of them right now to put in that password. By the way, folks, whether you see it or not, you are solving this case using a 6 here, or a 7 here, or an 8 here, or a 9. Remember when I branched off like this? 2 or 3? And then there was this method that I've used here. We're doing that here as well. And I would say this is much faster than branching off into 4 different calculations, right? Okay. Next, your code has to, sorry, there's a typo there, has to end in an even digit and start with a 2 or a 3. Repetition is allowed, okay? So we're going to go 2 or 3. It has to end with an even. Okay, so you've got 5 options here, and because repetition is allowed, you've got 2 options here because it has to do with 2 or 3, and then 10 here. You're back to 0 to 9. No worries about possibly repeating. That's what you fill in. So that would be 50 times 2. That's 100 passwords. There. Okay. Your code has to end in an even digit. Start with a 2 or a 3. Repetition is not allowed, so that complicates this a little bit. So here it is. Let's take care of the even part first. 2, 4, 0, 2, 4, 6, 8. Okay. In particular, folks, if you're going to use the 2 here, okay, if you're going to use the 2 here, can you start with a 2 up front here? Because repetition is not allowed. So technically you cannot start with a 2, so you'd have to start with the 3 here. And that's, so now you've used the 2 here, it's gone. You cannot use it anymore. The 3 is gone as well. So you're down to 8. There. So that's 8 passwords. Or if you start with a 2, then technically back here you only have these options to make this even, because you cannot repeat anymore. So you've got 4 here. So you got to fill out your restrictions first. You've used this one, you've taken care of that, you've taken care of that, you're left with 8. Okay, so 4 times 8 is 32. So combined, you've got 40 passwords that are possible. Okay, let's go up here and just say we cannot use these. I'm just considering, hold on. If I use a 3, then I actually have all 5 options here. Right? If I use a 3, I can use all 5 of these. So let's change this. I'm not going to post this one on YouTube. Anyways, 40 and 30, maybe I will, to show that we're all humans. Okay? 40 and 32 is 72. So you have to do cases here because of the conflict. The not repetition not allowed adds a layer of difficulty to it for sure. Okay? So you have all 5 that you can use here to make it even because you're using 3. But since you're using 2 here to start off, you're considering the one that starts with a 2. You cannot use it here, right? 2 is crossed out, cannot use it. So you're left with 4. So that's why it ends up being 72 passwords. Okay, let's go to 5. I'm going to hand this over to you for you to try. I'm just going to get you started here so you know how to deal with these types. Winnipeg postal codes consist of 3 letters and 3 numbers. For the numbers, we can use 0 to 9. For the letters, we do not use I and O. Why are I and O not used in a postal code, you think? But yeah, to not mix it up with 1 and 0. Yeah. So we cannot use it. So find the number of postal codes if the format is letter, number, letter, number, letter, number. That's the format. Okay? How many letters are there, by the way? 26, right? Okay. Make sure you know that. Down the road, we'll make a distinction between upper and lower case. Right? If it's case sensitive, you technically have 52 options. That's not the case right now, but that's coming. So letters 26. So if there are no restrictions, there should be a letter, a number, letter, number, letter, number, just to help you out, right? You don't have to do that, but I would strongly suggest you do. If we can't use I and O, we are really down to 24 letters available. So it says no restrictions, no further restrictions other than the I and O. By the way, folks, listen up carefully. Whatever is at the very beginning, whatever is stated at the very beginning, goes for all the other ones, A, B, C, D, E, F, G, whatever comes next. So the fact that we cannot use I and O stays. So from now on, we only have 24 letters. Okay? So we go 24, 24, and 24. Because it doesn't say we can't repeat, so 24 wherever there's a letter, and 0 to 9 is 10, right? 10 options. So you've got 10, 10, 10. and you basically just multiply them all. Here's a shortcut, in my opinion. How many 24s are being multiplied? 3 of them. And how many 10s? There's 3 of them as well. So entering it like that on your calculator is probably better. Just use the hat button. So you go 24 to the power 3 times 10 to the power 3, which is 1,000. If you remember that, that'll do it. So yes, our numbers are going to be pretty big. Okay, so this is 13,824,000 postal codes. Okay. What about no repetition allowed? I'm just going to leave this right now, let you struggle with it a little bit, because I know it's a bit of a painful experience, guys. I know that. It happens every year. But we will get through this. You just have to practice. The classic ones are your passwords, your postal codes. Those are the classic ones to start off with. And then we'll move on to different ones where, like, how many ways can you arrange a picture? People standing for a picture. We'll do that as well. So that kind of stuff. So I'm going to kind of slowly walk you through this unit. You just have to make sure you use a pencil, okay? And I will be back. I'll actually walk around. Passwords and all that was a bit crazy, I know that. I'm going to go over those tomorrow, okay? So you can rest assured I will do that. So page 9 and 10. Diagrams. If you need to practice that was what page on again. Let me just check. Page 3. If you need to practice tree diagrams, make sure you go there.